All right, this lesson is on real life inequalities. So you need your packet out in front of you, opened up to your notes page, and if you're not set up yet, please pause and get set up. But you need to listen well and make sure you're watching, paying attention to the examples. Remember, you should pause it at any point where you feel like something didn't make sense or something was going too fast. So there will be times when it's probably a good thing. Pause, catch up yourself, and then come back and unpause it when you're ready to go. All right, so the big ideas here, once again, about inequalities, they represent math statements that are not equal, okay? And they have lots of solutions, okay? They can have many solutions. And we're also going to look at graphing inequalities again, so it kind of answers this essential question: how does a graph on a number line best describe solutions to inequalities? Okay, we're going to revisit that topic some more. Now, we use inequalities a whole bunch in our day-to-day living, all right? There's a whole bunch of times where we see this, talk about this, understand this. It's just kind of built in. For instance, speed limits, they recommend that you go no more than 70 miles an hour. Or to be, at an amusement park, you need to be, at least this tall to ride a ride, or maybe some location has a maximum number of people that can fit in there. Or you're spending money and you can spend at most 60 bucks, or at the theater you have to be at least this age. Now notice I'm kind of emphasizing some words here because a lot of times when we talk about inequalities, we're referencing inequalities without even really knowing it, okay? Like if we say more than or exceeding or above or if something's greater than, you're probably talking about that inequality symbol. Or if we talk about at least, no fewer than, there's a minimum that you must have, the top number that is allowed. No less than, you're probably talking about the greater than or equal to symbol, okay? If you find phrases like fewer than or below or less than, you're probably referring to the less than symbol. And no more than or not above or does not exceed or at most or the bottom number, you're probably referencing the less than or equal to symbol. So we do this a lot with our language, with our speaking. Now, if I go back to that last slide, I kind of skipped it, but here's some examples. I mean, a suitcase must weigh less than 40 pounds. Like we can do some math with that. We understand its weight needs to be less than 40. You must be older than 12 years old to play something. Well, that means that you can be, 13 or 14 or 15, but older than 12. That means 12-year-olds wouldn't play that particular game or sport. You must be 12 years old or younger to order from the kids menu. All right, that's an example of, being 12 or 11 or 10 or 9. You're showing solution sets on graphs of an inequality, and you must be at least 40 inches to ride the roller coaster. So you have to be that tall or taller. All right, so there's a lot of ways this plays out in our life. So let's get right to your notes. Inequalities are often used when trying to solve problems. We use them a lot. All right, we're going to jump right into this first example. Sam is purchasing flags for his flag football team and can spend no more than $55. If each set costs $5.50, then how many flags can he purchase? Well, let's look at what we know. Sam is spending up to 55 bucks. It says no more than 55, so I just said up to 55. He can't spend more than that. He can spend exactly that. He can spend less than that. He just can't go over 55. The other thing we know is that each flag football set costs $5.50. All right, that's important as well. Now, what we need to know, what we're trying to figure out, how many flags can he purchase? All right, so fill those in and pause if needed. But let's get to our work here. So here's what we know. We know that the number of flags he's going to buy times 550, we want that value to be less than or equal to $55. Because again, we can spend up to 55 bucks. So this math problem could equal 55 or less. It just can't be more than $55. So if I show that with an inequality, that would just be like this. $5.50 times the number of flags needs to be less than or equal to 55. And now I have myself an inequality that I can solve in one step. So if I want to get the variable by itself, you ask yourself, what's happening to it right now? Well, it's being multiplied by 550. And we use inverse operations to get the variable by itself. So we would divide both sides by 550. And I want to do it over here, and I also want to do it over here, all right? And if I do that, I end up with a value of 11. We can buy up to 11 flags. So I used F for flags. The number of flags he can purchase needs to be less than or equal to 11. Because if he buys 11 flags exactly, then he would be spending 55 bucks. If he buys less than that, then he would be spending less than 55. But if he buys more than 11, now he's overspending. So this right here is our solution. What we want to do now is we want to graph that. So on the number line over here, we want to first think about the numbering of it, all right? And if he can buy up to 11, we're going to number close to 11. I put 11 in the middle, and I want 12 and 13 going this way, and 10 and 9 going this way. And I want to graph that. So I'm going to use a closed dot on 11 because he can buy 11. And remember, a closed dot means that we want to include that number. And we can buy anything less than it as well. We can buy 10 or 9 or 8, 7, 6, 5, 4, 3, 2, 1 down to 0. We can't buy more than it. So we have to go to the left with our arrow. That's going to show us our solution set. So what we have here is a problem that we had to break down. What do we know? What do we need to know? Let's figure this out. How many can he really buy? And then let's show it on a graph, okay? That's what we're going to be doing today. All right, number 2, Frances is saving money for a new Kindle. She needs to save at least, there's some key words, at least 200 bucks to pay for it, and has decided to save 25 bucks per week from babysitting. How many weeks will it be before she can purchase the new Kindle? Well, we know a couple things. She wants to save at least 200 bucks, and her plan is to save $25 a week. Now, what do we know, or what do we need to know? We need to know how many weeks it will be until she can purchase the Kindle, all right? So there's some math to be done, but we know a few things, and here's what we want to know. Now, think of it like this. If we know she's saving 25 bucks a week, and we know her goal is to get at least to 200, however many weeks she saves times 25, that needs to be more than or equal to 200 bucks. Because if it's not, then she can't buy her Kindle yet. So let's turn this into an inequality. Let's just take that 25 and multiply it by the number of weeks. And again, that should be greater than or equal to 200. So if I solve this inequality, again, think what is happening to our variable? Well, we're multiplying it by 25. So to undo it, we want to do the opposite of that. We want to divide both sides by 25. This side divided by 25 will leave us with W. This side divided by 25 will leave us with 8. We keep our inequality symbol the same. And we know that the number of weeks that they're going to save needs to be greater than or equal to 8. All right. So if I come over here on my number line, I put 8 in the middle. And I know that they need to save at least 8 weeks. Now they can save exactly 8 weeks. So I'm going to use a closed dot here, because if they saved 8 weeks, that would be 8 times 25, which is exactly 200. So 8 works. But the other thing here is that we want to show other weeks that they could also save. They could save for 9 weeks, 10 weeks, or 11 weeks, or so on. So our solution set is 8 and everything higher. 9, 10, whatever. It's not going lower because remember, if they save just for 7 weeks, they don't have enough money. Or 6, they don't have enough money. So that is our solution right there. It's a closed dot because we want to include 8 in our solution set. And it could also be more than that. So there's 1 and 2. I'm going to do a couple more with you, and then I'm going to release you to do a few on your own. Number 3, we're going to read these problems, define a variable, write an inequality, and solve for the missing number. So Jill received 45 ballots from the student council election. Mr. Alvarez, the advisor, drops off quite a few more, and Jill now has at least 250 ballots. How many ballots did Mr. Alvarez drop off? Well, the first thing they want you to do is to kind of define a variable. Remember, a variable would be what we're not sure of currently, all right? What we don't know. And if I look at the problem, there is one thing we don't know. Can you figure it out? We don't know how many ballots Mr. Alvarez dropped off and gave to Jill, okay? So I said that our variable, let's use X, just because it's X, and let's say it is the number of ballots Mr. Alvarez dropped off. Now, in our inequality, we really have this going on right here. She already had 45. Mr. Alvarez dropped off a bunch more, and all we know is that they now have at least 250. So we want to use this symbol because how many she has now is more than 250, or it might even be equal to 250. So that is our inequality. If we come over here and try to solve this one, well, again, we want to get the variable by itself. So it's being added with 45. So we undo that by subtracting 45 from both sides. And if we solve this, and if we solve this, we're left with X is greater than or equal to 205. So he dropped off at least 205 ballots, all right? So my numbers down here would be incorrect. I'm going to just kind of move this right here. You want to number these, maybe this is 205, and maybe this is 210, 215, maybe this is 200, and maybe this is 195. You can, whatever you count by, be consistent. I just used fives. But we also know that if that was 205, let me put this in there in the middle. If that was 205, he dropped off more than or equal to 205. So he dropped off numbers that are going this way on the number line, all right? That's our solution set for this problem right here. Number 4, let's go to number 4. Farmer Fran would like to build a chicken coop in order to raise chickens and sell their eggs. She determines that the area of the coop must be a minimum of 300 square feet. If the length of the coop is 12 feet, then how wide does the chicken coop need to be? So our variable would be what we are unsure of currently, the unknown piece of information. In this case, we know what the length is. We don't know what the width is, though. And that right there is going to be our variable. Now, a chicken coop very often is rectangular in shape. So if you think about finding the area for this, because we want it to be at least 300 square feet, area for rectangles is just length times width. Like its long side times its short side. That'll tell you how much area it has. So if we do length times width, we want that to have an area of at least 300 square feet, at least that much, all right? So if we want to solve this one, that's kind of what we were doing first, 12 times the width. So I just rewrote it, 12 times W. And if we want to get the variable by itself, what do we do here? Well, we divide this by 12. So over there, we'll divide that by 12. And that turns out to be W needs to be greater than or equal to 25. All right, so the width needs to be at least 25 feet. That's what we know. So we can come over here now, we can set up our number line, and we can put 25 in the middle. And again, my first question is, can the width be exactly 25? And the answer is yes. So a closed dot right on 25. But we also know that our inequality can be more than 25. So we want to go right. We want the numbers that are more than 25. All right. So this is our solution set for the width. It needs to be at least 25 feet. It can be any of these. It just can't be less than that. It can't be 24 because that would not give us an area of at least 300 square feet. Okay. All right. Here's what I want you to do now. Pause the screen and try the next 4 on your own. All right, there's a lot going on here, so come back when you're ready. All right, in number 5, our variable was how much he wants to spend per person. Because he knows that he wants to spend less than 175. So he's spending for 5 people. That's your variable. 5 times how much he's going to spend. He wants that to be less than 175. So that's our inequality. Now down here, I solved that. All right. I got the variable by myself by dividing by 5 on both sides. And I figured out that he really can spend up to 35 bucks per person. All right. Actually needs to spend less than 35 bucks per person. Because if he spends 35 bucks per person, he ends up spending more than he needs to, which I just realized I made a mistake. All right. This should be an open dot right there because he does not want to spend 35 per person. He wants to spend less than that. So that's what number 5 looks like. If we look at number 6, our variable was the number of dollars that they're wanting to use. Our inequality was x minus 155 needs to be greater than or equal to 2,500. All right, that's a 2 back there. But here's kind of what's going on. All right, they want to make a profit of $2,500, and they've already spent $155 just for the printing of the tickets. They want to make their profit plus that, really, which is why down here we really want to add these two numbers. So they want to make at least $2,655. And on a graph, that would look like this. My numbers here are off, but this should be 2,655. And this should be 2,645. All right, I was counting by tens, and for those every other one. So go ahead and check yours on that one, see how yours compare. In numbers 7 and 8, the variable was the number of students that are going to go on the field trip. The inequality was the number divided by 15. If that is the maximum number of people per group, then the number divided by 15 will tell us that how many groups we can have, and we want that to be less than 18 or equal to 18. So if we solve that, that would be what I see down here now. They can basically have up to 270 people go on the field trip. So if we graph that, they can have 270. That would give them exactly 18 groups, or they can have less than that. They can have 250, 200, 150, whatever. But that means our solution was really that again. X is less than or equal to 270 people. And at number 8, Skype charges a caller 30 cents per minute to call a landline in Cambodia. How many minutes could you call if you only had 21 bucks to spend? Well, our variable is the number of minutes you're planning on talking. That is what we don't know right now. Our inequality, well, that would be the number of minutes times 30 cents. And we want that to be no more than 21 bucks, okay? So we want that less than 21 or equal to $21. All right, so if we work with this right here, this is what your solution should have looked like. Let me move these. But if I solve that, I really came up with this. This is where that came from. If I divide by 30 cents on both sides, I end up with an X value that is needing to be less than or equal to 70. So that's the solution to our inequality. And we want to graph that. And they can talk up to 70 minutes. So a closed dot on 70, because if they talk 70 minutes exactly, it would be $21. Or they can talk less than that, 60 minutes, 50 minutes, or something in between. All right. All right, I'm just going to remind you about these words here. Very often these words kind of cue us for what symbol we're talking about. So that is something just to pay attention to. I don't know if you want to write those down or if you just want to pay attention to them when you see them, but they give us a glimpse of what symbol we're wanting to use in math context. All right, that brings this one to a close.